All right, this is example number 1. Okay, so the LSAT, a test taken for law school admission, has a mean score of 151 and a standard deviation of 9, and is unimodal symmetric, has a distribution of scores. So there's 2 test prep organizations, one that teaches a class of 9 students and another one that teaches a class of 25 students, and both organizations will publish their mean and standard deviation. All right, so when I'm doing this problem, I see a few things that I need to identify first. I'm given a mean score of 151, and I'm given a standard deviation of 9, and I'm told that this population is unimodal and symmetric. So looking at my values, I am told, okay, let me just change this back again. Okay, so I am told that my mean is equal to 151, and I'm told my standard deviation is equal to 9, and the population is unimodal and symmetric. Okay, so knowing that piece of information for part A, it asks, what would I expect the distribution for both of those organizations to be? Well, when we describe a distribution, remember we need to first talk about the shape. Okay, now the shape for both of those distributions are going to be exactly the same as the population because it's unimodal and symmetric. Okay, now the smaller the sample size, the more like the population the sampling distribution is going to look. So the n equals 9 case is going to look more unimodal and symmetric, and n equals 25, since it's bigger, is going to be even more unimodal and symmetric. The key here is, if we had a skewed distribution, we would want a larger distribution to make sure our sampling distribution is unimodal and symmetric. Okay, now let's move on to our centers. Okay, so for our mean of n equals 9, let's take a look at that one. So we have mu of x bar. Well, guess what? That equals the same as the population. And then for our 25, our mu of x bar is going to equal 151 again. And now for our spread, let's take a look at our standard deviation. So we have our sigma of x bar, and that's going to equal sigma over the square root of n. So that's going to equal 9 over the square root of 9, which equals 3. And then for my n equals 25 class, that is going to equal 9 over the square root of 25, which is going to be equal to 1.8. All right, for part B, if either organization has a graduating class with a mean score of 160, they'll take out a full-page ad in the local paper to advertise, which is more likely to have that success. So here's my key word in this problem, more likely. And we have a tool at our disposal to determine what's more likely to occur, and that's the z-score. So let's find the z-score for 9, the class of 9, and that's going to be 160 minus 151 divided by its standard error, or standard deviation, which is going to be 3. And when I do that, I'm going to get 3 standard deviations. And then when I find the z-score for the 25 class, I'm going to get 160 minus 151 divided by 1.8, and I'm going to get a z-score of 5. Now, 5 says this is more unusual. 3 says this is less unusual, even though it is unusual. So which is more likely to occur? The one that's less unusual. So the class with 9. And then part C, both organizations advertise that if any class has an average score below 145, they'll pay. So which one's at more risk? So again, greater risk. I'm going to look at z-scores again. So in part C, I'm going to take a look at the z-score for 9, and I'll take a look at 145 minus 151 divided by 3. And then for that one, I am going to get, I believe, -2. And then I do z sub 25, and I do 145 minus 151 divided by 1.8, and I get -3.3, I think. So again, the one that's at more risk is a smaller class size. Okay. All right, example 2. So using t-tables, software, or a calculator, estimate the critical value of t for 95% confidence interval with degrees of freedom of 7. All right, so in part A, we're going to find T critical value of degrees of freedom 7. So using your calculator, you're going to find the inverse T of 1 minus your confidence level divided by 2, 0.025, comma, your degrees of freedom. And then when you do that from your calculator, you're going to get 2.37, and that is your critical value. Or you can look at the table. All right, part B. So we want the T critical value for degrees of freedom of 102. So we're going to do inverse T. We want 1 minus the confidence level divided by 2. So that's how I get 1.005, comma, 102. And when I do that, I get about 2.63. All right, for part C, we want the p-value for T sub 41 is less than or equal to 2.19. So in the calculator, I'm going to use TCDF, and then I'm going to do negative E99 as my lower boundary. My upper boundary is 2.19, and my degrees of freedom is 41. And when I type that in, I get 0.9829. And then for part D, we want the probability or the p-value for an absolute value of T sub 12 is greater than 2.33. And that's going to be the same. This is absolute value, so that's a two-sided test, as 2 times the p-value of one of them. One side. Okay? So on my calculator, I'm just going to hit 2 times the TCDF of 2.33, comma, E99, comma, 412. And then that is how I get the p-value of 0.0381. Okay. All right, so here's example 3. So describe how the critical value T for 95% confidence interval changes as the number of degrees of freedom increases. Okay, so if you look at the column, and I'm just gonna real quickly pull that up. So I'm gonna go to my computer and pull up the T value. And you guys can just wait a second as I do that. Okay, so I'm going to my file, tables and formulas. Okay. All right, tables and formulas. And I'm just going to pull a screenshot of this table in just to show you how this works. Okay, so here we go. So here is a table. Okay. So let's see what's going on here. So here's the 95% confidence level. If you see right here, oh, I don't know if I can get off of there. Here we go. Here's the 95% confidence level. And here are my T critical values. So if you notice, we start off at 12.71. And what happens to these numbers as I continue to go down this column? That means my degrees of freedom increases. Okay, well, if you notice, my critical values decrease as my degrees of freedom increases, eventually getting really close to the Z critical value. So I'm basically going to write that up here, and I'll type that in so it's a nice, something you can read as opposed to me writing it, okay? So I would say the following. As the number of degrees of freedom increases, the critical value of T for a 95% confidence interval gets smaller, approaching approximately 1.960, which is the critical value of Z for a 95% confidence interval. Okay. All right, so here's example 4. So software analysis of salaries of a random sample of 288 Nevada teachers produced a confidence interval shown below. Which conclusion is correct? And what's wrong with the others? All right, so here's our confidence interval. The T interval produced is between 38,944 and 42,000 893. All right. So part A, if we took many random samples of 288 Nevada teachers, about 9 out of 10 of them would produce this interval. So part A is not correct, okay? So it's not correct because 9 out of 10 samples will produce intervals that contain the mean value. So this is not talking about intervals. 9 out of 10 of what, okay? All of them produce intervals, okay? It's about the intervals capturing the true mean that we want. Okay, part B. So if we took many random samples of Nevada teachers, about 9 out of 10 of them would produce a confidence interval that contained the mean salary of all Nevada teachers. Well, that's a correct statement. I would add the phrase of the same sample size. Okay. Sample 4, C. Okay, so about 9 out of 10 Nevada teachers earn between $38,944 and $48,893. This is incorrect because it talks about individual teachers. The interval talks about the mean. Okay. D, about 9 out of 10 of the teachers surveyed earned between $38,000 and $42,000. This is also incorrect because this is talking about a sample. The interval guesses what the true mean is. E, we are 90% confident that the average teacher salary in the United States is between this and this. This is wrong because this population says it's United States, where ours is Nevada. Okay. Number 5, based on meteorological data for the past century, a local TV weather forecaster estimates that the region's average winter snowfall is 23 inches with a margin of error of plus or minus 2 inches. Assuming he's used a 95% confidence interval, how should viewers interpret the news? Comment on each of the following. So during 95 of the last 100 winters, the region got between 21 inches and 25 inches of snow. Well, this is not correct. The confidence interval is not about years in the sample. Okay? It's about the true mean. B, there's a 95% chance that the region will get between 21 inches and 95 inches. Well, this is given a chance or a probability, so this is wrong. Okay? C, there will be between 21 inches and 25 inches of snow. Well, this is, again, not true. We're guessing what the true mean will be. D, residents can be 95% sure that the area's average snowfall is between 21 inches and 25 inches. That is true. And then E, residents can be 95% confident that the average snowfall during the last century was between 21 inches and 25 inches per year. Well, we don't know. We want the true average of all, average snowfall between, okay? So this is false. All right, example 6. The data collected by a child development scientist produced this confidence interval for the average age in which they begin to crawl. So the average age is between 29.202 and 31.844. The 95% confidence. Explain carefully what this interval means. All right, so let's go ahead and type that up. Okay. All right, and I'm going to increase my size here so we can see this a little bit better. All right, so in part A, I would say the following. We are 95% confident that the interval of 29.2 to 31.8 weeks contains the true mean age at which babies begin to crawl. All right, part B. What is the margin of error for this confidence? Okay, and then part C, we'll go ahead and answer that. Okay. All right, so for part B, what you do to find the margin of error is simply subtract the interval 31.844 minus 29.202, and you get about 2.6 weeks. Divide that in half to get just a margin of error, and you get about 1.3 weeks. Okay? All right, part C. Okay. It says if the researcher had calculated a 90% confidence interval, would the margin of error be larger or smaller? Well, the margin of error would have been smaller. Less confidence requires a smaller critical value of t, which decreases the margin of error. Right. So example 7. So a credit card company takes a random sample of 100 cardholders to see how much they could charge their last month. Here's a histogram. So they get a computer, they get the confidence interval. Explain what went wrong. Okay, so let's go ahead and try to explain what went wrong. All right. So the analysts did not find the confidence interval useful because the conditions for inference were not met. There is one cardholder who spent over $3 million on his card. This made the standard deviation, and therefore the standard error, huge. The t-interval is too wide to be of any use. Okay? So remember, one of the conditions for inference we always have to check is the histogram. It must be nearly normal. And this is clearly not nearly normal. All right, example 8. So hoping to lure more shoppers downtown, a city builds a new public parking garage in its central business district. The city plans to pay for the structures for parking fees. So during a 2-month period, which is 44 weekdays, daily fees collected an average of $126 with a standard deviation of $15. So A, what assumptions must be made for statistical inference? Okay, so let's go ahead and go through those processes. And I'm not going to write down the full one, but I'm just going to go through the little checklist here. So the first thing we must have is random. Okay. The weekdays were not randomly selected. So we will assume that the weekdays in our sample were representative of all weekdays. The next condition is 10%. So 44 weekdays are less than 10% of all weekdays. Okay, and then our last condition we need to check is our nearly normal condition. Okay, so we don't have the actual data, so that means we can't graph it to see if our histogram is nearly normal. But since the sample of 44 weekdays is fairly large, it's okay to proceed. And what does that mean, fairly large? Well, our n is basically greater than or equal to 40, which means it's fairly large. Okay. So the weekdays, so moving on here to part B, okay, we are told our n is 44, our sample mean is going to be 126, and our sample standard deviation is $15. Now, if I wanted to calculate my degrees of freedom, it would be n minus 1, and that's how I get 43, okay? So what I would end up doing is just go straight to the t-interval on your calculator underneath stat tests, type all those in, and the interval you get is 122.2 to 129.8. Okay. All right, so in part C, explain what this interpret this interval. So we would say we are 90% confident that the interval $122.20 to $129.80 contains the true mean daily income of the parking garage. Okay. Part D, what does 90% confidence means in this thing? So if many samples of size 4, were taken, we would expect 90% of confidence intervals produced, of those confidence intervals produced, to capture the true mean. All right, in part E, the consultant predicted that the parking average would be 130. Do we think he was correct? No, because 130 is outside our interval. All right. Example number 9. So suppose, for budget planning purposes, the city in exercise 18 needs a better estimate of the daily income for parking fees. So, A, someone suggests the city use a 95% confidence interval instead of a 90% confidence interval. How would this be better for the city? We don't actually have to calculate it. All right, so in part A, what would a 95% confidence interval do? So the 95% confidence interval would be wider. Okay, which means we would be more confident that we contained the true mean. Okay, this would be better for the city because we would be more likely to contain the true value of the mean. Okay, B, how would the 95% interval be worse for the planners? Okay, so since it's wider, okay, it would be less precise. Okay, thus more difficult for budget planners. Okay, part C. How could they achieve an interval estimate that would better serve their planning needs? So they could do a larger sample. Okay. What this does is it would decrease the margin of error without losing precision. Okay, and then D, how many days worth of data should they collect to have a margin of error of 3 to be 95% confident? All right, so let's use this formula. Margin of error equals Z star times S over the square root of N. So here we have $3 equals, and we'll use 1.960 times our standard deviation from the previous problem. That's going to be 15 divided by the square root of N. So solving, you get N equals, and you're going to have 1.960 times 15 over 3 squared. Okay, and let's go ahead and do that. So 1.960 times 15, enter, divide by 3, divide and square it. So we should get 96.04, and then we want to round that up to be 97. Okay. Now, if you want it to be a more precise one, we could calculate using a t-critical value of s over the square root of n. Okay, so again, using the same values, but this time use t-critical value for 96 times 15 over the square root of n. Okay, and I'm just going to use this in my calculator real quick. So second distribution, I'm going to go to inverse t, and we're going to use 95%, so 0.025 for my area. My degrees of freedom is going to be 96. I'm going to hit paste. All right. So I'm going to solve. So I get n equals, and this is going to be my critical value, which is going to be 1.985 times 15 divided by 3 squared. Let's see what we get here. 1.985 times 15, enter, divide by 3, enter. And let's square that value, and I get 98.5, which rounds up to be 99. All right, I'll take either answer there. And we're going to stop for that video there. All right.